Well, let's look at a worked example of a stereoisomerism problem where we've got two stereo centers in the compound. So here's the compound we're going to be working with, and we're going to be asking a bunch of questions about this compound. The first one is we need to find any chiral carbon atoms. We need to find out how many stereoisomers there are. We need to assign each chiral center either R or S. We need to name the compound, draw and name an enantiomer and a diastereomer, and figure out if any of the stereoisomers are meso. So I'm going to go through and explain each of those parts. Now before we get to that, I've got to explain what a Fisher projection is. Now a Fisher projection allows us to have any stereo center that happens to be in this configuration. I call it a bow tie configuration because you've got the two outs, you've got these two coming out and you've got these two going back. So east-west has to be coming out, north-south have to be going back. And if you've got that configuration, you can automatically just go ahead and write that as straight lines, assuming that that's the stereochemistry that it has. So given our example, we have that configuration, the bow tie configuration, here on both stereo centers. So we can go ahead and just write the whole thing with straight lines. That's going to make life so much easier for us because we don't have to show all this stereochemistry in all our diagrams. Alright, so here's our compound. Our first mission, we need to star any chiral carbon atoms. Now keep in mind a chiral carbon atom is any carbon atom that has four different things attached to it. It turns out this carbon's not chiral, or this carbon, because they don't have four different things attached. These two do. So this one, I'll star that one, and I'll star that one. So both of those are chiral centers. The next thing, how many stereoisomers are possible? Well, it turns out that there are going to be 2 to the n stereoisomers, where n is the number of chiral centers. So that's 2 to the power of 2, which equals 4. Had there been 3 chiral centers, there would have been 2 to the power of 3, which would have been 8. Now you might be wondering, where does the 4 come from? Well, I'll tell you. My 4 chiral centers comes from all the possibilities. We can have R, R, we can have S, S, we could have R, S, or we could have SR. That's a total of 4. But let's say it had been 2 cubed equals 8. That would be 3 chiral centers. Then that would be R, 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 S, 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 R, S, R, S, R, etc., etc. You can come up with the other 4 on your own if you'd like. But the point is that we have as many chiral centers as we have possibilities for those chiral centers. So we're actually going to be building 3 of these. We're going to be finding the initial one. We're going to be getting an enantiomer. We're also going to be getting a diastereomer as well. So we'll be getting 3 of those 4. Alright, so the next thing we need to do is assign each chiral center either R or S. And we need to draw the structure with the lowest priority group at the back. Well, presently, you need to understand that the back is going to be here and here for each chiral center. It's going to be this position and this position, because that's the position that's pointing backwards. So what we've got to be doing is trying to get the lowest priority groups on each of those chiral centers into the back. Well, the first thing is we know that hydrogen in any case is going to be the lowest priority group. That will be the group 4. I don't need to do any other math aside from that to know that that's the lowest priority group. So I know that my first aim in life will be to get the hydrogen into these positions here. Now, using a technique similar to the one I showed you in the Assigning Stereochemistry mini lecture, what we're going to do is we're going to leave this backbone untouched, and we're just going to rotate the groups around so that we're just sort of spinning this around this carbon-carbon backbone. So what I'll do is I'll get the lowest priority group into the back, and we'll handle each of these stereocenters one at a time. So we're going to handle the top one first. Oops. Right, this is the top stereocenter. And I'm going to try and get the lowest priority group into the back. Now, as you can see, if I move the hydrogen up here, the bromine goes over here and the CH3 goes over to here, that will allow me to reach my goal. Now I'm going to leave the bottom one alone for now. Come up with that in a second. Right now the lowest priority group is in the back. Now it's in the back, I can actually go ahead and figure out the stereochemistry of the top chiral center. That's the only one I can look at right now. So what I'll do is I will assign priorities to each one of these. Now here is the carbon I'm actually interested in. This is the one I'm actually assigning. Attached to this carbon we have a bromine, we have a carbon, we have another carbon, and we have a hydrogen. Hydrogen is obviously the lowest priority group. We're not interested in that. So we've got a Br, a C, and a C. The Br wins automatically out of those three. Next, we look at this C. So we've got a C. The highest priority group attached to this C is a Br. The highest priority group attached to this C is an H. This group wins. So that's priority 2. And this here will be priority 3. Now each of these is considered a group attached to the chiral center. 1, 2, 3. So when I do the order, I find out that it's clockwise. So the top chiral center will be assigned R. Now what I'm going to do is I'm going to redraw this compound. And I'm going to put the lowest priority group in the back on the bottom one. So we're just interested now in the bottom chiral center. Now again, I'm not interested in the top. I've already fixed that up. Let's look at the bottom. Now what I've got to do is move the hydrogen into the back. So the hydrogen needs to go here. That means the Br is going to move where the CH3 is. And the CH3 is going to move over where the hydrogen was. Now we have the lowest priority group in the back for the bottom chiral center. So attached to the bottom chiral center I have a Br, a C, and a C. The Br wins out of those two. Next, I compare the C's. I've got a C here, I've got a C here. The highest priority group attached to this C is a Br. The highest priority group attached to this C is an H. This one wins. So this is going to be priority 2, and this is going to be priority 3. Again, these groups attached to the chiral center become the groups that we're comparing. So 1, 2, 3. Again, clockwise in order for 1, 2, and 3. the bottom one also is going to be R. Alright, so what we've done is we have identified the stereochemistry of both chiral centers. What I'm going to do now is combine both of those and show you the stereochemistries just as we figured them out. This one is R and this one is R. So there's our assigned structure with the lowest priority groups in the back. Alright, you can see I've taken the same approach in that case as well. Alright, the next thing we need to do is name the compound. Now, before I name it, I think it's probably going to be a good idea if I draw it out as a line structure. Now, finding these line structures is half the battle. So we've got a C, then we've got a C here, and we've got a C here. So what I'm going to do is I'm going to express this as a line structure. And remember, when we're expressing line structures, we ignore hydrogens attached to any carbon atoms. So that's what it would look like. Let's make it look a little prettier now. And this could then be named, and we would number the chain. Now remember, numbering the chain's got nothing to do with the priorities we were numbering earlier. This is just for the purposes of naming, and this would be called, this is an R, this is an R, this would be 2, oops, start again, it would be 2R, 3R, in parentheses, 2,3 dibromo butane. In this next part, we're going to find the enantiomer of this compound. So there's our compound. We've got R and R here. And to get an enantiomer, the best or easiest way to do it is just to get a mirror image. So that's a mirror. And the mirror image is going to look like this. And to get the signs, the stereochemistries, it's always just going to be the opposite of what it was before. So the mirror image is just going to have the exact opposite designations on this chiral centers. So that's the enantiomer right there. Now the name would be 2S, 3S, then everything we had before, the 2,3 dibromobutane. the next part of this is we need to find a diastereomer. Now a diastereomer is a situation where one of the chiral centers gets switched and one of them remains the same. Now we can actually do this on the original compound, or we can do it on the enantiomer, because the enantiomer of the diastereomer is also a diastereomer. So let's go through this one here and see if we can get a diastereomer. What I'll do is I will leave the top one the same and I will flip the bottom one. Now to get the diastereomer, I can just flip two of the groups attached to the chiral center. Just move the CH3 over here and move the Br over here. If I do that, that'll switch the R to the S. So this is an enantiomer. And this will be a diastereomer. So I'm going to leave the top the same and flip the bottom. That will just leave this an R and turn this one into an S. So all I did was just flip the bottom two here. I can flip any two atoms I like, but only two atoms. So this is a diastereomer. And the name of it would be 2R3S, and then the same name as before. Now if I had wanted to, I could have gotten the other diastereomer by leaving the bottom the same, leaving that R, and flipping these two on top, and that would be S. And the name of that one would be 2S 3R, and that would be the other diastereomer. But generally speaking, you're only after one diastereomer in these kinds of problems. The last problem is to identify a meso structure. Now a meso structure is a compound that has chiral centers but is actually achiral because there is a plane of symmetry in the compound. Now if you look at the original structure, you'll see that there is no plane of symmetry. If I've tried to put a plane of symmetry through here, the Br and the CH3 wouldn't match up. But the diastereomers are actually both meso compounds because there is a plane of symmetry right through the center of the compound. The Brs and CH3s match up. It turns out that if we try and put this into a polarimeter, it's going to turn out to have 0 degrees of rotation. What actually happens is that one chiral center rotates polarized light one way and the other one rotates it the other way, cancelling out its effect. So while it appears to be chiral, because it's got two chiral centers, the whole molecule is actually achiral. So this is actually a meso. And the other one is also meso, the other diastereomer. But the enantiomer and the original compound are not meso compounds.